Hi everyone. So today what I wanted to do is just go through a bit of a review of topic 4 before our test. So I'm going to start by going through a few of the questions from the practice test that I sent you guys. You should already have written solutions, but I'll just work through some of those solutions. And then at the end, I'll go through just a little bit of a summary of the things that you need to tick off and know. So the first question that I've got here is about writing balanced equations and looking at the insoluble products for the following reactions. Okay, so what we've got here are the reaction between two ionic substances. Okay, we've got potassium chloride and silver nitrate as our first one here. And what you guys need to be able to recognize here is that when we've got two ionic substances, what we're going to have is a double replacement reaction. So this is the reaction where they're essentially going to swap cations and anions with each other. Okay, so if we look at potassium chloride, the first thing we've got to do when we're looking at a reaction like this is write the molecular formulas for both of these compounds. Okay, so you guys should be able to know and work out what ion potassium will form and what ion chloride will form. And that's going to come predominantly from your periodic table. Potassium is a group 1 element, so it's going to form a +1 ion. So potassium is going to form this. Chloride is group 7, so it's going to form a -1 ion. Okay, silver is going to form +1. Okay, some of these metals, the transition metals, are a little bit trickier to work out. But what you guys will have in the test is this, which is our common ion and solubility table. So all of those ions will be on there for you to be able to look at as well. And that's what we're going to use to work out the solubility later. So then we have to work out the nitrate ion. And from our table, we can see that nitrate is NO3 negative. So knowing what these ions are helps us to determine what the molecular formula of these ionic substances are. Remember, the compound overall has to have a neutral charge. Okay, so potassium is a +1, chloride is a -1. So potassium chloride is just going to be one of each. Okay, plus silver nitrate, again, they're both +1, -1. So we only need one of each ion. Okay. So what we've got to do now, we know that when this reaction occurs, they're going to swap ions, okay? So the positive ion, potassium here, is going to go with the negative ion nitrate, okay? So we're going to have potassium nitrate, okay? Again, they're only a +1 and -1, okay? So we only need one of each, plus, what are we going to have? We're going to have silver chloride. Okay, so now what we've got to do is we've got to work out, first we've got to make sure that everything's balanced, and because we only needed one of each, they're all +1 or -1 ions, everything is balanced straight away. Okay, so now we need to work out which one's the insoluble product. So the two products formed here are potassium nitrate and silver chloride. Okay, so we need to use this solubility table here to work out which one of these two will be insoluble. Okay, so let's have a look at nitrates first. All nitrates are soluble. Okay, so potassium nitrate we can eliminate straight away as being the insoluble product. Okay, that's not going to form our precipitate. Silver chloride, let's have a look at chlorides. Okay, all chlorides are soluble except for silver, mercury and lead. Okay, so that's great. That tells us that the silver chloride is going to be, oops, I'll move that back, going to be the solid, so we can put our little S in brackets. And what that actually means for our reaction here is that, let's go back to here. What this means, if we're going to write the proper ionic equation here, is that our potassium and our nitrate are actually still going to be dissociated in solution. Okay, so this is going to be aqueous. Okay, so what we're actually going to have here still is potassium and nitrate ions in solution. Okay, and then we're going to have our silver chloride, which is the solid, which precipitates out of that solution there. Okay, so in this case, we could say, because all of these are going to be aqueous to start with, AQ, The spectator ions in this case are potassium and nitrate because they don't actually react as such. They're still going to be ions in that solution there. Okay, so let's look at the next one here, barium nitrate and copper sulfate. So again, for barium might be one that you might not be familiar with. So you can go over to your common ions table here and you can work out that barium here we go, barium is our 2+ ion, okay? So knowing that, we know, let's just write the ions first. Barium is 2+, nitrate is -1. Copper is going to be 2+. Now, copper you have to watch out. It can be it can be a +1 or +2. Sulfate is going to be -2. Okay, so barium is a 2+ and nitrate is only a 1 negative. So we're going to need 2 nitrates for every 1 barium. So the molecular formula is going to be this for barium nitrate. Remember when we've got those polyatomic ions, which is nitrate is polyatomic because it's got more than 1 atom in it. When we're having multiple of those ions, we need to put them in brackets and put the number outside the brackets if we've got multiple lots of those. Okay, so there's our barium nitrate plus copper sulfate. Now copper and sulfate both, copper's 2+, sulfate's 2 negative. So copper sulfate is just going to be like this. Okay, so now we can work out the products. Barium is now going to go with the sulfate. Now barium is a +2, sulfate is a -2. Okay, so we don't need to do anything else with those. And we do, however, need to do something here. So then we're going to have copper nitrate. Now copper is a 2+, nitrate is only a -1, so we're going to have 2 of those nitrates again. Now we just need to make sure that all of this is balanced. We've got 1 barium, we've got 2 lots of the whole nitrate ion here, and we've got 2 lots on this side. We've got 2 lots here, 2 lots here. Copper, we've got 1 and 1, and sulfate, we've got 1 and 1. Okay, so our equation is balanced there. So now again, we need to work out what our insoluble product is going to be. So we've got barium sulfate and copper nitrate. Not all nitrates are soluble. Okay, so again, that rules out copper nitrate is going to be the one that's existing in solution still, dissociated. So the ions are going to be dissociated. Barium sulfate. So if we go to sulfates here, all sulfates are soluble except for barium, strontium, and lead. Okay, so barium is an insoluble sulfate. So this one over here, barium sulfate, is going to be the solid. That's going to be the one that forms the precipitate in this case. Okay, so let's go to the last one. Just move that over. Is magnesium chloride and sodium carbonate. All right, so again, magnesium is a 2+ ion, chloride is a -1, sodium is a +1, and carbonate is a -2 ion. Okay, so here we've got some more complex molecular formulas because we've got ions with different charges on them. Magnesium is a 2+, chloride is only a -1, so we're going to need 2 chlorides for every 1 magnesium. Okay, because it's a monoatomic ion, okay, we don't need to have the brackets around the ion this time. So we've got magnesium chloride plus sodium carbonate. Now again, sodium is a +1, carbonate is a 2 negative, so we're going to need 2 sodiums for every 1 carbonate. Okay, these are both aqueous, so don't forget those little things. I didn't include them in all of the reactions above. Okay, so again, here we're going to have swapping ions going on. So we're going to have the magnesium ending up with the carbonate. Magnesium is 2+, carbonate is 2 negative, so we're only going to need 1 of each. Okay. Sodium and chloride are going to end up with each other, and both of those are only +1, -1. Okay, so we only need one of each in the molecular formula of that one as well. Now here's where this one, we need to make sure that we've balanced everything properly here. So magnesium, we've got 1 on each side. Chloride, we've actually got 2 on the left-hand side and only 1 on the right-hand side. So we're going to need 2 lots of that sodium chloride there. Okay, that helps us here too because we've also got 2 sodiums on the left-hand side, but now we've balanced that there. Okay, carbonates, we've got 1 on each side, so everything is now balanced. All right, so now we need to work out what the insoluble product is again, and that's how we're going to use our table here. So we've got sodium chloride. I think we should all know that sodium chloride is soluble, okay? And our table up here confirms that for us. All chlorides are soluble except silver, mercury, and lead. And our second product is magnesium carbonate. Okay, all carbonates are insoluble except sodium, potassium, and ammonium. Okay, so the carbonate, magnesium carbonate, is going to be the one there, which is the solid product. Okay, and that is going to be the one that forms a precipitate in that case there. Okay, and I think, let's just double check the question and state the insoluble product. Okay. So obviously with these questions, if you were asked this type of question in a test, I would then want, it's actually asked you to state the insoluble product. So I'd want you to say, follow up on the end of each one with barium sulfate is insoluble. Okay, just to make it 100% clear that you understand what's going on there. Okay, so now what we're going to do is we're going to talk about some more calculations. So the first one here says, let's determine the concentration of the following solutions. Okay, and this one says 0.4 moles of copper sulfate dissolved in 200 mils of water. So like with any of these questions, the first thing that I do is write down what information we know. Okay, so it gives us the number of moles this time. So the number of moles equals 0.4. Okay, and the volume equals 200 mils. Now the volume's 200 mils, but remember we always want things in litres, so that equals 0.2 litres. Okay, so now we need to look at what it's asking us for, and it's asking us for the concentration. That's what we want to know. Okay, so now we know that we've got to go to our equation, which says N over V equals concentration. So now what we're going to do is have a look at what we know. Concentration is going to be equal to our moles, 0.4, divided by our volume, which is 0.2. Okay, and then we can calculate that on our calculator. So 0.4 divided by 0.2 equals 2. Some of you guys should have been able to do that in your heads. I should have too. Okay, so our concentration, remembering our units of concentration, it's going to be moles per litre. That makes sense because our top number here was in moles and our bottom number here was in litres. Okay, so that's that one. All right, so let's have a look at the next one on the next page. All right, so chlorine gas reacts with ammonia. Okay, so we've got this reaction here. Here's the ammonia, here's the chlorine gas, and these are the products formed, hydrochloric acid and nitrogen. Okay, so it's giving you the reaction for the equation, the question, and it's asking you to determine the mass of chlorine required to completely react with 20 grams of ammonia. Okay, so what we've got here, and what we might you might hear this referred to in some of the questions, is a limiting reagent. Okay, so we know exactly how much ammonia we've got, and so we want to know, if we surround this with chlorine gas, what is the mass of chlorine gas that we actually need? We might actually have excess chlorine gas, which means we've got way too much than we need, but we want to find out exactly how much we would need to react with this amount of ammonia. Okay, so you might hear sometimes in questions something referred to as the limiting reagent, And that will be the one that determines, according to the molar ratio, the limiting reactant will be the one that there is less of. Okay, so that will be the one that you have less of. So you can only perform as much of the reaction that you can with that limited amount of that reagent that you have. And that's why it's called the limiting reagent. So what will happen is you would have leftover of the other reactant, which doesn't react because all of the limiting reagent has already reacted. Okay, so let's get back to the question here. Determine the mass of chlorine required to completely react with 20 grams of ammonia. Okay, so first we need to think about what we know. And the only thing that we really know here is the mass of ammonia, okay, which is 20 grams. All right, so we want to know the mass. So if we make a little table, this is ammonia. We want to actually find the mass of chlorine, okay? Mass of chlorine is what we want to do. Okay, so how are we going to get from there? Well, one thing we do know is we can calculate the molar mass of ammonia. Okay, so our molar mass of ammonia is going to be nitrogen. So if you look at your periodic table, nitrogen is 14.01. Okay, 01 plus, and you're going to need 3 hydrogens, which is 1.008. Okay, so we're going to add all of that up, and we've got 3 times 1.008 plus 14.01. We've got a molar mass of 17.034. Okay, once we've got the grams per mole, remember our units. Once we've got the molar mass, we can now work out the number of moles that we have of ammonia. Okay, so remembering that our moles is equal to mass divided by molar mass. Okay, so what we're going to do then is our number of moles of ammonia is going to be equal to 20 divided by 17.034. So what that gives you is 1.17 moles. Okay, so if we've got 1.17 moles of ammonia, this is now where we have to go back to the stoichiometry in the equation. Okay, and what the equation tells us is that for every 2 moles of ammonia, we need 3 moles of chlorine to react with it. Okay, so if we know that we want to react all of the ammonia there, we need enough chlorine so that all of this ammonia will react. Okay, so we've got a 2 to 3 ratio here basically. So what I like to do, the way I like to do it, is I will, let's just move this. I will firstly take my 1.17 moles and I'll divide it by 2, okay, because that's the coefficient up here in front of the ammonia. Divided by 2, which gives me 0.59, okay. Then what I'll do is I'll times it by 3, which is the coefficient in front of the chlorine there. 1.761. And this is our moles of chlorine that we've got. Okay, so all I've done is I've taken the 1.17 moles of the ammonia and I've used the ratio in the equation 2 to 3 to convert that and work out how many moles of chlorine that I would need. Okay, and if we look at this, the 1.17 to the 1.761, that's a 2 to 3 ratio there. Okay, so now we know that the number of moles of chlorine that we need is 1.761. And if we want to work out the mass, so we're going to need the molar mass as well. So the molar mass of chlorine is going to be 2 times 35.45. which equals 70.9 grams per mole. Okay, so to work out the mass, I'm I'm just going to go down a little bit. So the mass of chlorine is going to be the moles, which is 1.761, multiplied by the molar mass, which is 70.9 times 1.761, which equals 124.85 grams of chlorine. Okay, so this is the mass of Cl2 that we need to react completely. Okay.